Hello everyone, this is the first part of the lectures devoted to cross-coupling reactions. We will start this module with a general introduction describing the importance and history of cross-coupling chemistry. Let's begin with some definitions. What type of transformations can be called cross-coupling reactions? There are many interpretations for that, and the most common explanation states the following. In organic chemistry, a cross-coupling reaction is a reaction where two fragments are joined together with the aid of a metal catalyst. Here is a general reaction scheme describing cross-coupling reactions. Most of the known cross-couplings involve highly significant carbon-carbon bond-forming processes. These are fundamental transformations, as the molecules of life are predominantly based on carbon-carbon bonds. As a rule, the reaction is based on the coupling of a main group organometallic compound, shown in red, with an organic halide, shown in blue. The reaction is enabled by late transition metals, which normally operate in combination with bulky and electron-rich ligands. The most frequently used catalysts are based on palladium. If your organometallic compound is an organoboron or an organosilicon reagent, then for their activation, you will need a base. Most of the cross-couplings you will learn today are name reactions and are defined by the used nucleophilic coupling partner indicated in red. For instance, cross-couplings based on organoboron reagents are called Suzuki coupling. Reactions with organodine reagents are known as Stille coupling. When the nucleophile is an aniline, the reaction is called Buchwald-Hartwig amination. Most of the known cross-coupling reactions have very similar mechanisms. The generally accepted mechanism for palladium-catalyzed reactions is depicted here. It involves most of the elementary reactions we learned during the last module of the course. The reactions are normally initiated by palladium-0 complexes, which means that if a palladium-2 pre-catalyst is applied, it is reduced to its active form before entering the catalytic cycle. The reaction is initiated by the oxidative addition of the palladium-0 pre-catalyst to the aryl halide or pseudohalide, generating this palladium-2 intermediate. The next step can be slightly different for various cross-couplings. If the next coupling partner is an organometallic compound, then oxidative addition is followed by transmetallation, generating a palladium-2 intermediate bearing fragments from both coupling partners. The last stage of the process involves reductive elimination, resulting in carbon-carbon bond formation regenerating palladium-0 species, which can re-enter the catalytic cycle. Cross-couplings catalyzed by nickel or copper have more complex mechanisms and will not be covered in this lecture. To answer the question about why do we need to study cross-coupling reactions, we need to assess some numbers. This chart shows the number of publications and patents on the most common cross-coupling reactions over the last 3 decades. Color codes are used to differentiate the name reactions from each other, as depicted on the right side of the chart. For instance, the columns in dark orange show the number of publications on Suzuki coupling, while the black columns indicate the publications on Sonogashira coupling. As you can see, from the early 2000s, there has been exponential growth in the field. This growth is directly related to the design and implementation of new highly active catalysts and ligands, which will be discussed later in the module. This field of research is dominated by the studies on Suzuki coupling. Over the last decade, more than 20,000 works have been published, dealing in some way with Suzuki coupling. Between 2001 and 2011, the number of publications and patents on Suzuki coupling was more than 10,000. The second and third most popular transformations are Heck coupling and Sonogashira coupling, respectively. Other couplings are less popular but still grabbed considerable interest. In 2016, an interesting work appeared in the Journal of Medicinal Chemistry, which was about the analysis of past and present synthetic methodologies used in medicinal chemistry. In the work, the authors analyzed the most frequently used reactions in medicinal chemistry, covering the years 1984 and 2014. This chart summarizes the results of the study, where the red columns represent the occurrence and percentages of a given reaction in the year 1984, while the blue columns refer to the distribution of popular reactions in 2014. As you can see, the Suzuki coupling is the second most frequently used reaction in medicinal chemistry. 19% of the works published in 2014 cover the Suzuki coupling at least once. Buchwald-Hartwig amination and Sonogashira coupling are also in the top 20 most frequently used reactions for drug discovery. It is noteworthy that cross-coupling reactions had limited applications in 1984, as this field of research was still in its infancy. On top of the traditional cross-couplings, Amide bond formations and ester formations nowadays are frequently realized by carbonylative cross-coupling reactions. In this work, the authors raise another legitimate question. Where have all the new reactions gone? You see, medicinal chemistry predominantly is based on well-established and reproducible reactions, which exhibit good functional group tolerance. Unfortunately, these factors are not always inherent to the modern super-duper transformations published in the Journal of the American Chemical Society or other high-impact journals. Versatility, reproducibility, and the possibility to construct all sorts of carbon-carbon and carbon heteroatom bonds are perhaps what made this field so popular and eventually led to the Nobel Prize Award in Chemistry for the year 2010. Now, we can go through some history and see how this field of research has emerged and evolved. In addition, I will guide you through specific details of some cross-coupling reactions. The development of cross-coupling chemistry conventionally can be divided into 3 periods. The first wave of developments involved the discovery of cross-coupling as a concept, the first attempts to realize this chemistry in a selective fashion, and the elaboration of the first catalytic transformations. This spanned more than a century, from 1869 to 1976. The second wave of developments took almost 2 decades and was focused on the expansion of the scope of coupling partners. This was the period when more versatile organometallics based on metalloids were introduced. The third wave of development started in 1995 with the discovery of the Buchwald-Hartwig amination and is still in progress. Here, the main focus of the research was and is on the continuous improvement and extension of known cross-couplings through rational design and fine-tuning of ligands. This chemistry is older than you could possibly imagine. It has a rich and intriguing history with some of the oldest transformations in organic chemistry dating to the 19th century. The earlier discoveries in the field were the metal-mediated homocoupling processes between 2 structurally identical fragments, which set the foundation for the later discoveries. Cross-coupling chemistry began in 1869 when Glaser described the oxidative dimerization of a previously prepared copper phenylacetylide to give a diphenyl-diacetylene in an open flask. Following the development of homocoupling of sp-hybridized systems, the copper-mediated methodology was extended to carbon-carbon bond-forming reactions of sp2 hybridized systems. In 1901, Ullmann reported the dimerization of 2-bromo and 2-chloronitrobenzene promoted by the use of superstoichiometric copper powder. The key difference between the Glaser dimerization of acetylenes and the Ullmann homocoupling is that the latter is based on the use of pre-functionalized or halogenated systems. The use of halogenated organic molecules turned out to be a common theme for the following developments in the field. Later, in 1914, Bennett and Turner demonstrated that Grignard reagents also can be dimerized in the presence of stoichiometric quantities of chromium-3 chloride. A few years later, Turner also reported an analogous homocoupling reaction promoted by copper-2 chloride. Despite these remarkable achievements, the early metal-promoted reactions were limited in 3 key ways. First, stoichiometric metal reagents are poorly soluble in common solvents because of that the reactions are slow and require harsh conditions. Second, the reactions are not selective. And finally, the reactions include pyrophoric reagents and demonstrate poor functional group tolerance. The first glimpses of a solution to these issues appeared during the first half of the 20th century. Although catalytic quantities of copper had been shown to promote the carbon-oxygen coupling reaction of phenols with aryl halides as early as 1905, the use of catalytic amounts of metals for the formation of carbon-carbon bonds somehow remained an elusive concept during the first part of the 20th century. In 1939, Meerwein was the first to report the effects of catalytic copper-2 salts on the coupling of aryl diazonium salts with cinnamic acids. However, Meerwein's groundbreaking studies appear to have been lost in time, and even now there are only 226 citations of his work. The first systematic investigation of transition metal-catalyzed carbon-carbon coupling is found in a 1941 publication by Karash, which describes the cobalt-2 catalyzed coupling of Grignard reagents with aryl halides. In subsequent studies, this work was extended to the cross-coupling of vinyl bromide with aryl organomagnesium species. These studies represent not only the earliest reports on catalytic cross-couplings but also the first selective carbon-carbon bond-forming reactions based on 2 different coupling partners. After this point in the history of coupling chemistry, a set of standard requirements for coupling processes became apparent. In the broadest sense, any coupling procedure required 3 components to achieve a selective cross-coupling event: an organohalide, as a coupling partner, a stoichiometric organometallic partner, to prevent homocoupling of the organohalide coupling component in a transition metal in catalytic quantities to affect the carbon-carbon bond forming event. These components would prove to be the guiding principle in coupling chemistry to this day. The utilization of palladium-based catalysts significantly facilitated the developments in the field and set the grounds for the discovery of other important cross-couplings. Palladium was discovered by Wollaston more than 2 centuries ago, but all the efforts from Wollaston to get a profit out of palladium were unsuccessful. The first catalysts on palladium were palladium on charcoal and Lindlar catalysts. These catalysts are used for selective hydrogenations of unsaturated systems and are commonplace in research laboratories even today. As a result, it quickly became evident that catalysts on palladium demonstrate high affinity and activity for double and triple bonds. The first palladium-catalyzed cross-coupling was the arylation of olefins, which is frequently called Heck coupling. In the late 60s, Richard Heck was employed in a company heavily invested in the commercialization of the palladium-catalyzed oxidation of olefins, known as the Wacker process. This is where he got interested in the potential application of olefins and palladium catalysts for the development of a new cross-coupling reaction. The first successful results came when he treated organomercury compounds with olefins in the presence of a palladium catalyst and air. It was clear that due to the high toxicity of the organomercury reagents, alternative procedures are highly desired. As a result, a few years after Heck's initial report, it was demonstrated that aryl halides also can be successfully olefinated with palladium catalysts. The new methodologies required stoichiometric amounts of a weak base and an inert atmosphere. Over the following decades, a vast number of groups would demonstrate the high functional group tolerance and wide applicability of the new methodology. Presently, the Heck coupling has a unique place in the arsenal of methods available for organic synthesis. The mechanism of Heck coupling is slightly different from other couplings. Among the known cross-couplings, only the Heck reaction does not involve a transmetallation step. The oxidative addition of the aryl halide to the catalytically active palladium-0 species initiates the catalytic cycle. At this stage, the processes diverge. In the Heck coupling, the reaction progresses by coordination of an alkene to the palladium-2 species, which is followed by a syn-migratory insertion. The regioselectivity of this insertion depends on the nature of the alkene, the catalyst, and the reaction conditions employed. The newly generated organopalladium species then undergoes syn-β-hydride elimination to form the alkene product. The active form of the catalyst is regenerated by reductive elimination of an acid, which is neutralized by the base. Until the mid-1970s, the field of acetylene coupling was dominated by the use of copper salts as catalysts. However, in 1975, the palladium-catalyzed coupling of acetylenes with aryl or vinyl halides were concurrently disclosed by the groups of Kasser, Heck, and Sonogashira. The coupling conditions reported by Sonogashira, employing copper co-catalysis, that made the reaction conditions exceedingly mild when compared to the copper-free methodologies from Kasser and Heck. The reaction demonstrates high functional group tolerance as it requires a weak organic base and mild conditions. Thus, the Sonogashira coupling is frequently applied as a late-stage coupling strategy in the synthesis of complex molecules. For the Sonogashira coupling, there are 2 catalytic cycles operating together. The deprotonation of acetylene is assisted by copper and leads to the in situ generation of the corresponding copper acetylide. The latter undergoes a transmetallation with the palladium-2 intermediate, regenerating the copper catalyst. The reductive elimination of the product from this palladium acetylide intermediate regenerates the palladium-0 catalyst, which can undergo another oxidative addition in the next cycle. It is important to highlight that the reaction is highly sensitive to air. In the presence of oxidants, copper acetylide intermediate instead of transmetallation can form notable amounts of a byproduct diacetylene via Glaser coupling. A common limitation of both organomagnesium and organolithium coupling partners was the inherent intolerance of sensitive functional groups due to the reactive nature of these anionic organometallic species. Thus, in the years surrounding Heck's discoveries, chemists sought to find less reactive anionic organometallic reagents. In 1977, Negishi and Juten reported the use of organozinc reagents in cross-coupling reactions. It was demonstrated that organozinc reagents can tolerate many functional groups, including nitro group and carbonyl compounds, which was unheard of for Grignard reagents. Subsequent findings indicated that magnesium and lithium could be replaced with other metals and some metalloids, which might be capable of participating in the proposed transmetallation step in the catalytic cycle involving palladium. The first metalloid demonstrating meaningful rates for transmetallation to palladium species was tin. The first report on the synthetic utility of organometallic reagents for cross-couplings came from the group of Mijita. They demonstrated that for palladium-catalyzed allylation of aryl bromides, one can apply allyl-tributylstannane. Later, the group of Stille unveiled the synthesis of ketones by coupling acyl chlorides with organostannanes under significantly milder reaction conditions than those reported by Mijita. In the early 1980s, Stille further explored and improved this reaction, developing it into a highly versatile methodology displaying remarkably broad functional group compatibility. This reaction was among the first cross-couplings used in total syntheses, which, in turn, changed the ways that chemists thought about carbon-carbon bond construction. Without argument, the main disadvantage of the Stille coupling is the toxicity of organostannanes. To address this issue, the studies on the development of alternative organometallic coupling partners were expanded further. Here, a short historical context can help us to understand better the process of the discovery of Suzuki coupling. In the early 60s, inspired by the research on hydroboration of unsaturated systems, Suzuki moved to the group of Herbert Brown for a short postdoctoral study. Herbert Brown was one of the founders of this field of research, which eventually was recognized by awarding the Nobel Prize in Chemistry in 1979. Organoboron compounds are quite different from other organometallic compounds. Compared to organomagnesium or organozinc reagents, they are chemically inactive, have low nucleophilicity, and rather behave like Lewis acids. Organoboron compounds are stable in the presence of water and alcohol and do not undergo typical Grignard-type reactions. Therefore, it was believed that such compounds would not be suitable coupling partners for transmetallation in palladium-catalyzed cross-coupling reactions. Organoboron compounds were previously examined by Heck and Negishi, however, without much success. Heck even observed that boronic acids can be competent cross-coupling partners, but only when stoichiometric quantities of palladium are employed. In 1979, Suzuki, having recently returned to Japan from his postdoctoral studies with Brown, resolved this issue with a clever solution. He found that organoboron reagents can become excellent coupling partners for transmetallation when treated with stoichiometric quantities of a base. The base is required for the activation of boronic acids, which are Lewis acids. The transmetallation is effective only when this type of boronate complex is formed from the reaction of the base with the organoboron reagent. In fact, the base normally plays a dual role. In addition to the activation of boronic acids, it activates the palladium-2 intermediates by substitution of its X-type ligand, which is normally a halogen. Now let me describe the factors making Suzuki coupling special. First of all, boronic acids, including different hybridization states of the carbon, are readily available. There are many relatively mild methods for the regioselective hydroboration of olefins and acetylenes. Aromatic systems also can be effectively borylated using either Miyaura borylation or direct CH borylation enabled by iridium catalysts. The resulting organoboron starting materials are easily handled and usually are stable under air and in the presence of moisture. Carbon atoms in all hybridization states can undergo carbon-carbon bond-forming reactions when using Suzuki couplings. Last but not least, typical Suzuki couplings offer mild and convenient reaction conditions and demonstrate remarkable functional group tolerance. In fact, the functional group tolerance of the reaction is indirectly controlled by the inorganic base used. A hallmark of the Suzuki discovery was the demonstration that bases can activate organometallics based on metalloids, allowing the coupling of organometallic reagents unable to undergo transmetallation under standard conditions. This discovery pointed to the possibility of uncovering coupling reactions of other organometallics with lower electronegativity differences between the metal and the organic moiety. Building on this knowledge, in 1988 Hiyama and co-workers described the palladium-catalyzed coupling of organosilanes with aryl halides and triflates. For the activation of organosilanes, they applied a number of fluoride bases, including cesium fluoride. The Hiyama coupling provided a more environmentally friendly and safe approach than other couplings, as the main byproducts of the reaction are silicates. The 90s witnessed the evolution of non-carbon-based nucleophiles participating in a cross-coupling process, thus adding new dimensions to palladium-catalyzed processes. The first palladium-catalyzed formation of carbon-nitrogen bonds was disclosed by Mijita and co-workers in 1983. The major limitation of this method was the use of stoichiometric amounts of toxic, as well as heat and moisture-sensitive tributyltin amide reagents. In 1995, Buchwald and Hartwig independently replaced the Mijida-amido-10 reagent with a free amine. The reaction was effective exclusively with bulky phosphine ligands and only worked in the presence of strong, bulky bases, such as lithium bis, trimethylsilyl, amide, and sodium tert butoxide. The mechanism of the reaction is slightly different from the couplings involving organometallics. The oxidative addition step is followed by coordination of the amine to the palladium-2 intermediate as an L-type ligand. The coordination increases the acidity of the amine, which is being deprotonated by the base and turns into an X-type ligand, amide. The final step of the process is the reductive elimination of the aryl amine and regeneration of the palladium-0 active catalyst, which enters another cycle. To sum it up, in this lecture, you were introduced to the main classes of cross-coupling reactions. I presented a historical perspective on the three main waves of developments in this field, which is still underway and presently is focused predominantly on the development of novel catalytic systems via rational design and well-tuning of ligands controlling the activity of palladium catalysts. These and other relevant topics will be described in the following lectures of the module. Thank you for your attention. Greetings to all, and welcome back to the series of lectures on cross-couplings. This lecture will cover the most significant developments in the design of phosphine ligands enabling cross-coupling reactions. Some classical tertiary phosphine ligands are shown here. Phosphines are among the most important ancillary ligands in homogeneous catalysis. All transition metals, particularly late transition metals, form complexes with phosphines. They are soft donors and match well with soft acceptors like late transition metals. The substituents on the phosphorus atom can be easily manipulated, which, in turn, can dramatically affect the properties and reactivity of the metal center. This will be demonstrated in the following. Phosphines are more susceptible to oxidation than amines because phosphorus in the +5 oxidation state is stable. Many alkyl phosphines are air-sensitive and even pyrophoric. Considerably less electron-rich aryl phosphines and phosphites are less sensitive or indefinitely stable to air. Additionally, more sterically hindered alkyl phosphines are less air-sensitive than less hindered alkyl phosphines. An amine containing 3 different substituents will consist of a racemic mixture of conformers in solution, but most phosphines containing 3 different substituents can be prepared in an optically active form. This is largely because the barrier to inversion at phosphorus is much higher than the barrier to inversion at nitrogen and typically ranges from 29 to 35 kilocalories per mole. P-chiral phosphines can be resolved and stored indefinitely as pure enantiomers. William Knowles, a laureate of the Nobel Prize in Chemistry for asymmetric hydrogenations, did most of his studies on p-chiral phosphines. In general, phosphines bearing 3 alkyl groups are the most electron-donating among the dative phosphorus ligands. Aryl phosphines are less electron-donating as the greater S character of the sp2 hybridized orbital of the aryl group makes it a weaker electron donor than an alkyl group. Similarly, phosphites, which contain 3 alkoxy groups at phosphorus, are the least electron-donating ligands because the electron donation by the alkoxy groups is weaker than that by alkyl or aryl groups. There are several approaches available for quantifying the donor abilities of phosphines. In a classic study, Tolman measured the values of IR stretching frequencies of CO ligands and corresponding nickel-carbonyl complexes using infrared spectroscopy. Here, L is a phosphine or phosphite being studied. The values of IR stretching frequencies of CO ligands depend on the degree of backbonding to the CO ligands. The degree of backbonding depends on the electron density of the metal center, which, in turn, relies on the electron-donating ability of the phosphine and the nickel-carbonyl complex. Some representative frequencies for the IR stretching of CO ligands are presented in the table. The higher the wave numbers, the weaker the donation you have from the L ligand. These data show that tritert-butylphosphine and tricyclohexylphosphine are the strongest donors in the set. In general, alkyl phosphines tend to be stronger donors than aryl phosphines, and phosphorus trifluoride is the weakest donor in this set of phosphorus ligands. Alternatively, the electron-donating ability of phosphines can be quantified from carbonyl complexes of other metals or by measuring the phosphorus-selenium coupling constant of corresponding phosphine selenites. The steric properties of phosphorus ligands have been exploited many times to control the reactivity of organometallic compounds. Tolman can again be credited with an early systematic treatment of the steric properties of phosphorus ligands. Tolman devised a structural parameter he called the cone angle, which is the angle defined by the outer edge of the substituents at phosphorus and the metal center of a space-filling model, as shown here. This work was conducted well before computer modeling and computational energy minimization procedures. Nowadays, to measure a cone angle, you must have an X-ray crystal structure of a gold complex of your ligand. Based on this data, the cone angle is estimated computationally. The modern alternative for the cone angle is called buried volume, which is more frequently used for quantifying the steric bulk in heterocyclic carbene ligands. For chelating ligands, the steric hindrance caused by the ligand is quantified by measuring the bite angle. The bite angle is the ligand-metal-ligand bond angle of a coordination complex containing a bidentate ligand. The magnitude of the bite angle depends on the size and flexibility of the bridging linker between the two phosphine atoms. For comprehension, here are some common chelating ligands with corresponding bite angles. The larger the bite angle, the more sterically hindered the system will be. For instance, DPPF has the largest bite angle among these ligands and is one of the most successful ligands in cross-coupling chemistry. This diagram summarizes the stereoelectronic properties for a range of phosphines and phosphites. The higher the ligand is positioned, the less electron donating it is. The ligands positioned far to the right are the bulkiest systems, while the ligands positioned to the left are not sterically hindered. During the early years in the development of cross-coupling reactions, the readily available triphenylphosphine and catalysts based on triphenylphosphine were the systems of choice. As the possibilities of improving reaction conditions and increasing substrate scope by changing the organometallic reagent progressed, the nature of the employed ligand became recognized as the most important variable for controlling the activity and selectivity of the used catalyst. In 1979, Kamada was the first to note the beneficial effects of the bidentate ligand DPPF in the palladium-catalyzed coupling reaction of alkyl Grignard reagents with organic halides. Note that DPPF has one of the largest bite angles among chelating ligands. Before this observation, alkyl organometallics possessing hydrogen atoms at the beta position were practically useless for cross-coupling chemistry. The first reports from Buchwald-Hartwig on the arylation of aliphatic amines were based on tri-orthotolyl phosphine, which has a relatively large cone angle. A year after their initial report, it was shown that with ligands having a large bite angle, the Buchwald-Hartwig amination of aryl bromides can proceed even at room temperature. BINAP was examined by Buchwald, while DPPF was tested by Hartwig. You should remember from the lectures on elementary reactions and homogeneous catalysis that the reduced selectivity of cross-couplings for alkyl organometallics and aliphatic amines is caused by β-hydride elimination. These unwanted side processes require a syn conformation for the catalyst and the beta hydrogen, which is normally suppressed by bulky monodentate ligands or chelating phosphines with large bite angles. The next wave of developments in cross-coupling chemistry was initiated by the discovery of the crucial role of the electronic properties of phosphines in the catalytic activity of palladium catalysts. In 1998, the group of Fu demonstrated that electron-rich and bulky phosphines can enable Suzuki coupling involving a series of unreactive aryl chlorides. Their work was predominantly focused on the application of tricyclohexylphosphine and tritert-butylphosphine. 2 years later, the group led by Beller introduced D-adamantyl, N-butylphosphine as a prominent ligand for cross-couplings involving unreactive aryl chlorides. Beller's ligand outperformed tritert-butylphosphine for this reaction and was effective even when used in ppm quantities. Gradually, researchers started to map the effects of the used ligand upon the steps in the catalytic cycle, including oxidative addition, transmetallation, and reductive elimination. First, it was found that in the case of bulky monodentate phosphines, the maximum number of ligands that can coordinate to palladium 0 is 2. Remember that palladium 0 needs coordination of 4 L-type ligands to have 18 electrons in the bonding shell and become coordinatively saturated. This means that palladium complexes of bulky ligands are normally coordinatively unsaturated. Notably, when heated, these complexes can lose one of the bulky ligands and act as a monoligated palladium 0 species, which is even more coordinatively unsaturated. This type of monoligated palladium 0 species is stabilized by the bulkiness of the connected phosphine and is easily approachable for aryl electrophiles and oxidative addition reactions. In addition, the electron-donating alkyl groups on the phosphorus atom increase electron density on the palladium center and enhance the rate of oxidative addition. Here, The effect of bulky, sigma-donor ligands on the activity of palladium catalysts is demonstrated using the example of palladium complexes based on tritert-butylphosphine. However, all the activating effects and ways of action described for tritert-butylphosphine are inherent for other bulky donor phosphines. For instance, coordinatively unsaturated and monoligated palladium species were described for many phosphines developed by Buchwald. Little is known about how ligands facilitate or inhibit transmetallation. It is widely accepted that bulky ligands promote transmetallation by favoring coordinatively unsaturated palladium intermediates, as shown here, which allows the approach of the nucleophile to the metal center. Note that the monoligated palladium species remain coordinatively unsaturated even after the oxidative addition. Following the transmetallation, the halogen anion on palladium, represented as X, is substituted by another nucleophile, which is normally much larger than the leaving X group. As a result, the large alkyl substituents on the phosphorus atom force the palladium intermediate to release the strain of the system through the reductive elimination of the product. This, in turn, regenerates the monoligated palladium-0 species for another catalytic cycle. The unprecedented reactivity of palladium catalysts embodied by bulky, sigma-donor ligands prompted Buchwald and his colleagues to develop a new generation of phosphines that could be easily tuned and modified. This would offer new opportunities for the rational design of the activity and selectivity of catalysts used in cross-coupling chemistry. The ligands introduced by Fu and Beller possess only aliphatic groups, limiting the possibilities to modify their stereoelectronic properties. Having at least one aryl group connected to the phosphorus would solve this issue, as the stereoelectronic properties could be tuned by various substituents on the aryl group. As mentioned earlier, the group led by Buchwald demonstrated that amination of aryl bromides can proceed even at room temperature when using catalysts based on BiNAP. In fact, they decided to develop bulky, sigma-donor phosphines based on BiNAP. First, they substituted the binaphthyl system with a biaryl to have better control over the effects caused by the introduced functional groups. Then, they substituted one of the phosphines with weakly coordinating groups or non-coordinating bulky substituents. The introduced substituents prevent unwanted cyclometylations, hamper the free rotation of the aryl group, and enhance the bulkiness of the system. This turned the bidentate ligand into a bulky monodentate phosphine. To maintain the bulkiness and strong sigma-donor properties, they substituted aryl groups at phosphorus with tertiary or secondary alkyl substituents. For further control over the stereoelectronic properties of the developed phosphines, they introduced various functional groups at this aryl substituent. Over the early 2000s, they developed 3 generations of phosphines with various degrees of steric bulk and sigma-donor abilities. Now, most of these phosphines are commercialized and named after the students who first developed them. It should be noted that XPhos is the most frequently used ligand in homogeneous catalysis. It is universally active for different cross-coupling reactions. RetPhos and RuPhos demonstrate unique selectivities in Buchwald-Hartwig aminations. RetPhos is particularly useful for amination reactions involving primary alkylamines and anilines, whereas RuPhos mostly enables aminations with secondary amines. Over the last decade, they have developed the 4th generation of biaryl monophosphines for more specific applications. With these phosphines, they have increased the degree of bulkiness and complexity to a new level. Buchwald's phosphines have shown broad applicability in a diverse array of cross-coupling reactions, which will be described in the following lectures. The reactivity of catalysts supported by these ligands is influenced in complex ways by the ligand architecture, as summarized here. The large substituents on phosphorus lend stability to the ligands by slowing the rate of oxidation of the phosphorus atom. This feature makes these ligands even more practically useful in synthetic chemistry, as they can be stored under ambient conditions. The bulkiness of the ligands also facilitates the formation of monoligated palladium complexes and enhances their relative stability. The lower aromatic ring can serve as a ligand for the palladium center, further stabilizing the monoligated palladium intermediates. Substituents R3 and R4 enhance catalyst stability by suppressing cyclometallative pathways for deactivation. The presence of R3 also serves to favor the conformation in which the palladium sits over the bottom ring. This facilitates the rate of reductive elimination and enhances the stability of catalytically important intermediates. The electron-donating or withdrawing properties of the R3 substituent serve as an additional factor for controlling the electronic properties of the ligand. In the early 2000s, Hartwig adapted a similar strategy for the development of bulky and strong sigma-donor phosphines based on DPPF. To enhance the bulkiness of the system, they introduced a range of non-coordinating groups instead of the bottom diphenylphosphine. The bulkiness and sigma-donor properties of the phosphine were further controlled by the implementation of alkyl and aryl substituents with varying steric hindrance. Here, some of the phosphines prepared in the group of Hartwig are presented. Most of them have proven to be successful ligands for cross-coupling reactions and other transformations. Q-phos is the most famous ligand from the list and is commercially available. On top of the traditional phosphines described above, I want to highlight some important ligands introduced recently. Tri-adamantyl phosphine was believed to be the bulkiest phosphine and was not available until the report of Caro in 2016. However, the analysis of the stereoelectronic properties of tri-adamantyl phosphine revealed quite surprising results. Measurement of the buried volume from the corresponding gold complex showed that tritert-butyl phosphine is bulkier than tri-adamantyl phosphine. The electron-donating abilities of the ligand were quantified from the values of CO vibrations of the corresponding rhodium-carbonyl complex. Tri-adamantyl phosphine exhibits unexpectedly strong electron-releasing characteristics that exceed other alkyl phosphines and fall within a range dominated by N-heterocyclic carbons. We will discuss the properties of N-heterocyclic carbons in the next lecture. Here, you just need to know that N-heterocyclic carbons are normally better sigma donors than phosphines. The concept of increasing the ligand donor strength reaches its limits with the use of trialkyl-substituted phosphines, with tri-adamantyl phosphine being one of the most sigma donor ligands. Ylides have a special donor strength to stabilize electron-deficient, low-valent main group compounds. This phenomenon has led to the realization that ylide-substituted phosphine ligands might possess remarkably strong donor abilities. As a result, the electron-donating abilities of phosphines were enhanced to a new level after the introduction of the ylide-substituted ligands by the group of Gessner. It is worth mentioning that the ylide-substituted phosphines are highly tunable by changing the nature of the groups on the phosphonium, phosphine, or central ylidic carbon atom. In particular, a comparison of the Tolman electronic parameters with those of other ligands showed that ylide-substituted phosphines are generally more electron-donating than classical phosphines and can partly compete with N-heterocyclic carbons. As ylides are generally stronger donors than alkyl groups, the diyllidyl phosphines have the strongest sigma donor abilities among the known phosphines. The percentage buried volumes measured for ylide-substituted phosphines indicated that they are more sterically demanding than most phosphines and, in this sense, are similar to biaryl phosphines. To sum it up, in this lecture, you were introduced to the main phosphine ligands used in homogeneous catalysis. You learned about the importance of the stereoelectronic properties of phosphines and how the steric hindrance and sigma donor properties of ligands control the activity of late-transition metal-based catalysts. You were introduced to Buchwald's ligands and other groups of highly active phosphines enabling cross-coupling reactions. In the following lecture, we will concentrate more on N-heterocyclic carbons and examine their role in the development of homogeneous catalysis. Thank you for your attention. Greetings to all and welcome back to the series of lectures on cross-coupling chemistry. So far, you have been introduced to the main principles of cross-coupling technologies and the most successful phosphine ligands enabling these reactions. In this lecture, we will concentrate on the design of the main families of N-heterocyclic carbene ligands used in homogeneous catalysis. N-heterocyclic carbons or NHC ligands are a class of stable singlet carbons with a neutral divalent carbon atom directly attached to at least one nitrogen within a heterocyclic scaffold. There are two major groups of N-heterocyclic carbons. The first group includes carbons based on imidazoles, abbreviated as NHC ligands. The second group of carbons is based on pyrrolidine. They are often named cyclic alkylamino and abbreviated as CAAC ligands. N-heterocyclic carbons were first described in 1968 by Ophel. It was found that when heated, imidazolium salts, possessing a mixed chromium hydride carbonyl counteranion, lose a molecule of hydrogen and generate an NHC chromium carbonyl complex. This discovery was a mere accident as Ophel obtained the NHC chromium complex while aiming to purify the parent imidazolium salt by sublimation. These ligands received little attention after their initial description. However, interest in NHC ligands increased exponentially after the isolation and characterization of the first free carbene. which was shortly followed by the first demonstrations of the utility of N-heterocyclic carbons as ligands for homogeneous catalysis by Hermann. Compared to other classes of carbons, NHC ligands are remarkably stable. Simple carbons decompose above cryogenic temperatures, cyclopropanate alkenes, dimerize, and insert into otherwise unreactive CH bonds. In contrast, NHC ligands can be stored, bottled, and even distilled. Although NHC ligands still do not surpass the stability of classic phosphines such as triphenylphosphine, and typically must be stored under an inert atmosphere. Presently, many NHC ligands are commercialized and sold protected in the form of CO2 adducts or imidazolium salts. Free carbene ligands can be generated from CO2 adducts by heating, while imidazolium salts generate corresponding NHC ligands upon treatment with a strong base. N-heterocyclic carbons are present in nature and play a central role in enzymatic catalysis. Thiamine, otherwise known as vitamin B1, is a protected N-heterocyclic carbene and can be deprotected by a base. In nature, thiamine acts as an effective organocatalyst, enabling asymmetric aldol condensations and related transformations. It has been proven that thiamine can also serve as an effective NHC ligand for metal-catalyzed reactions. Initially, N-heterocyclic carbons were thought of merely as phosphine mimics. However, with each passing year, the difference between phosphine donor ligands and NHC ligands becomes more and more apparent. N-heterocyclic carbons are particularly good ligands for the late transition metals and are normally better sigma donors than phosphines. As such, the metal NHC bond is typically stronger than the corresponding metal phosphine bond. In fact, the bond strength in the NHC ruthenium complexes has been estimated by calorimetric methods to be double that of corresponding phosphine ruthenium bonds. Similar observations were seen for nickel NHC and nickel phosphine complexes. NHC ligands are singlet carbons, which means that they have one empty p orbital parallel to the lone pair orbitals of nitrogens and one perpendicular sp2 hybridized orbital filled with 2 electrons, notably nucleophilic and available for sharing with a metal for complexation. In NHC ligands, 2 electronic effects work in parallel, determining the stability and sigma-donating ability of the ligand. Nitrogens share their lone pairs with the empty orbital of the carbene, which, in turn, decreases the pi-accepting abilities of the ligand. In other words, NHC ligands do not participate much in backbonding and do not decrease the electron density at the coordinated metal. Nitrogens, being more electronegative than carbon, decrease the electron density at the carbene by sigma electron withdrawing. This phenomenon increases the energy separation between the singlet and triplet ground states and contributes to the further stabilization of the carbene. This diagram shows the comparable sigma donor abilities of different carbene ligands. Cyclic alkylamino carbons are among the strongest donors known to date, as the sigma electron withdrawing from the carbene is done by only one nitrogen. The pi-accepting abilities of NHC ligands also strongly depend on the number of nitrogens stabilizing the carbene. Carbons based on imidazoles have 2 nitrogens connected to the carbene atom, resulting in higher stabilization of the empty p orbital due to the delocalization of 2 lone pairs of electrons with the empty orbital. Consequently, cyclic alkylamino carbons exhibit enhanced pi-accepting properties since they have only one nitrogen atom for the stabilization of the empty p orbital of the carbene. Therefore, cyclic alkylamino carbons demonstrate a pronounced duality. They are both the best sigma donors and the strongest pi acceptors among the classical NHC ligands. The pi-accepting abilities of NHC ligands can be further increased by the introduction of electron-withdrawing groups around the nitrogen atoms, as demonstrated in the underlined examples. The backbonding in carbons is best illustrated in ruthenium catalysts used for olefin metathesis. Here, we can examine a representative example from the Hovey de Grub's second-generation catalysts, where ruthenium is simultaneously bound to 2 carbons. The NHC-ruthenium bond is better described as a single bond since the backbonding in these systems is not prominent due to the stabilization of the empty p orbital of the carbene by the lone pairs of nitrogens. This stabilizing effect is illustrated by the inclusion of a curve between the nitrogen atoms. In contrast, the second ruthenium-carbene bond is more accurately described as a double bond, as the empty p orbital of the second carbene is not stabilized by neighboring groups or atoms. The methods for quantifying the stereoelectronic properties of NHC ligands are numerous and very similar to those described for phosphines. The most common method is based on estimating the overall donating capability of NHC ligands using Tolman electronic parameters, specifically the IR stretching frequencies of CO ligands and model transition metal complexes. Originally developed for phosphine ligands and widely employed in the investigation of NHC ligands, this method is not without some intrinsic limitations and does not fully characterize the pi-accepting effects of the ligand. Alternatively, the analysis of NMR signals from the main group nuclei involved in the corresponding NHC complexes provides a valuable experimental tool for evaluating the pi-accepting properties of carbene ligands. The two main methods, which generally yield comparable results, are based on comparing phosphorus and selenium NMR chemical shifts for appropriate adducts of carbons with phosphorus and selenium. Phosphines and NHC ligands have similar electronic structures, but there is a significant difference in their topology when coordinated to the metal center. The three substituents of the phosphine project backward, away from the metal, thereby forming a cone, while the substituents on the NHC nitrogen atoms project forward to form a pocket around the metal center. This arrangement in the case of NHC ligands allows the topology of the substituents to have a much stronger impact on the metal center. The steric properties of phosphines are primarily characterized by their cone angle. However, this may not be the most suitable metric for NHC ligands, as they tend to be less symmetrical, and their steric impact can be unevenly distributed. To address the lack of useful and quantitative descriptors for evaluating and comparing the steric impact of NHC ligands, the concepts of percent buried volume and steric maps have been developed. These can be measured exclusively through DFT calculations or, alternatively, based on crystallographic data obtained for a given ligand. The percent buried volume is defined as the percentage of a sphere around the metal center occupied by a given ligand. This metric does not require the ligand to adopt a symmetrical geometrical shape and can describe mono and polydentate ligands, as well as phosphines with phosphorus bearing more than one type of group. While the percent buried volume quantifies the steric profile of a ligand, it provides limited detail regarding the specific arrangement of this steric impact. To address this limitation, steric maps were introduced, offering a way to represent and visualize the steric profile of NHC ligands, particularly unsymmetrical ones. Steric maps display, through colored contours, the steric bulk presented to the metal center, dividing it into quadrants. These maps help appreciate how the steric impact is distributed throughout space, identifying features such as catalytic pockets and potentially revealing the origin of enantioselectivity for certain catalysts. Here are some commonly used NHC ligands with calculated percent buried volumes. The greatest steric hindrance is observed in systems with large groups attached to the phenyl rings connected to the nitrogens. The comparison of percent buried volumes for NHC ligands with various ring sizes is presented. The larger the ring of the NHC ligand, the bulkier the system, as these large rings cause the phenyl groups connected to nitrogens to approach the metal more closely. Here is presented a general structure for an NHC ligand-based palladium precatalyst. It offers numerous possibilities for tuning and modifying the activity of the system. To ensure the stability of the catalyst, the groups connected to the nitrogens must be bulky. Otherwise, there is a risk of deactivation through cyclometallation involving R3 groups. However, this does not mean that you must always have bulky groups here. For bulky substrates, the use of non-bulky NHC ligands is typically beneficial. Additionally, in controlling the sterics and stability of your catalyst, you can adjust the sigma donor properties of the ligand. If you aim for a strong sigma donor NHC ligand, then R3 groups must be either alkyls or arones possessing electron-donating groups. When working with bulky substrates, it might be beneficial to have non-bulky R3 groups connected to nitrogens, combined with functional groups at positions 4 and 5 of the imidazole ring. Extra functional groups in the ring can restrict the free rotation of R3 groups without significantly altering the sterics of the system. Additionally, you can significantly change the pi-accepting abilities of the ligand by introducing strong electron-withdrawing groups. For instance, carbonyl groups will reduce the pi electron donation from the lone pairs of nitrogens to the empty p orbital of the carbene. The bulkiness of the ligand can be increased or decreased by adjusting the ring size. It is worth noting that saturated NHC ligands are better sigma donors compared to their corresponding unsaturated analogs. For this particular palladium-based precatalyst, you can enhance the kinetics of dissociation of the supporting pyridine ligand by using systems with either bulky or electron-withdrawing substituents at the pyridine ring. Here, it is worth recalling how stereoelectronic effects influence the elementary reactions of cross-couplings initiated by palladium-phosphine complexes. As you may recall, in the case of bulky phosphines, the active forms of the catalyst are coordinatively unsaturated monoligated species. The strong sigma-donor phosphines facilitate oxidative addition, and the bulkiness of the system is crucial for reductive elimination. All of these factors are equally important for reactions enabled by palladium catalysts incorporating bulky NHC ligands. The first step in the couplings initiated by NHC-palladium complexes involves the activation of the pre-catalyst. For this specific pre-catalyst, this includes the dissociation of the supporting pyridine ligand and the reduction of palladium-2 to the active palladium-0 form. The reductant can be either the organometallic reagent present in the reaction media or other reagents. In the case of bulky NHC ligands, the active form of the catalyst is a coordinatively unsaturated, electron-rich system that undergoes oxidative addition with the electrophilic coupling partner. It is important to note that NHC ligands are typically better sigma donors than phosphines, facilitating oxidative additions, even with challenging substrates like aryl chlorides. Following oxidative addition, the system remains coordinatively unsaturated, which supports the transmetallation. During transmetallation, the catalytic system becomes strained because the nucleophile substituting the X ligand on palladium is usually larger than the X ligand. Consequently, the bulkiness of the NHC ligand promotes reductive elimination, leading to the product and the formation of the active form of the coordinatively unsaturated palladium-0 intermediate, initiating a new cycle. There are several thousand NHC ligands reported to date, playing a central role not only in cross-coupling chemistry but also in olefin metathesis, organocatalysis, and other fields of homogeneous catalysis. Presented here are the most frequently used NHC ligands along with their corresponding abbreviated names. Most of them are commercially available and are typically sold in protected forms, which include imidazolium salts or CO2 adducts, as mentioned earlier. The strong binding of the electron-rich carbene to the metal center makes NHC-palladium complexes particularly stable. As a result, reasonable alternatives to the protected NHC ligands are corresponding well-defined palladium complexes presented here. Some of them are palladium-0 complexes and do not require reducing agents for preliminary activation. Others are palladium-2 complexes with additional ligands that can easily dissociate or undergo reductive elimination, generating active NHC-palladium-0 species. Inspired by the astonishing activity of the Grubb's third-generation catalyst in olefin metathesis, Organ and co-workers developed a family of air-stable and user-friendly palladium NHC pre-catalysts based on bulky carbons and easily dissociating 3-chloropyridine. Organ's palladium NHC complexes are commercialized and abbreviated as palladium Pepsi complexes. They have developed several generations of palladium Pepsi complexes by systematically increasing the steric bulk at the ortho positions of the infinite moieties of the NHC ligands. To sum it up, in this lecture, you were introduced to the main groups of NHC ligands used in homogeneous catalysis. We examined the stereoelectronic effects influencing the stability and potency of N-heterocyclic carbons as ligands for late transition metals. In particular, it was demonstrated how the stereoelectronic effects of NHC ligands can be well-tuned and modified for targeted applications. You also saw that a practical method for the protection and storage of NHC ligands is the preparation of corresponding well-defined metal complexes. This is a good point to stop, as the following lecture will concentrate on the use of pre-formed catalysts in cross-coupling reactions. Thank you for your attention. Welcome everyone to the continuation of our lecture series on the latest advancements in cross-coupling reactions. In the previous sessions, we delved into the fundamentals of cross-coupling reactions and explored key ligands pivotal for generating highly active catalytic systems. In this lecture, we will delve into a crucial aspect of this field, focusing on the most significant preformed catalysts and their representative applications. The efficiency with which the catalytically active, monoligated palladium-0 complex is formed before entry into the catalytic cycle is a key factor. In the selection of reaction conditions for palladium-catalyzed cross-coupling reactions, if a palladium-2 salt, such as palladium acetate, is used, reduction of palladium-2 to palladium-0 must occur before the cross-coupling reaction can take place. This reduction can be achieved by the amine component in an amination reaction, especially if the amine possesses hydrogen atoms alpha to the nitrogen atom, enabling the palladium-2 amine complex to undergo beta-hydride elimination. Alcohols can similarly reduce palladium-2 to palladium-0. Phenylboronic acid or other organometallics are also capable of reducing palladium-2 pre-catalysts. In this case, a transmetallation to palladium-2 is followed by reductive elimination of phenylacetate, generating a palladium-0 active pre-catalyst. If primary amines, alcohols, or boronic acids are not present in your reaction mixture as substrates, you can still consider adding them in catalytic quantities for the activation of palladium-2 pre-catalysts. The phosphine ligand may also influence the reduction of palladium-2 through reductive elimination of phosphonium salts, such as phosphonium acetate, generated in the case of palladium acetate. However, this process is likely slow with bulky, electron-rich phosphines. Traces of water can be beneficial for the reduction of palladium-2 species mediated by a phosphine, as water can hydrolyze phosphonium acetate to phosphine oxide, making the process irreversible. Therefore, it is recommended to use a slight excess of a phosphine over the palladium-2 source, as part of the used ligand can be consumed for the reduction of the pre-catalyst. Until the early 2000s, the most frequently applied catalytic systems used to be generated in situ by mixing a palladium precursor with a ligand. The most common palladium sources were palladium acetate and palladium dibenzylidine acetone complexes. However, this strategy for catalyst generation has several notable drawbacks. First, it was noted that the DBA ligand can have a poisoning effect on the catalyst. Although palladium acetate and palladium dibenzylidine acetone complexes are readily available palladium precursors, their purities vary significantly, depending on their preparation and supplier. In addition, many of the highly active electron-rich phosphine and NHC ligands are air-sensitive and can be deactivated by oxidation before the in-situ generation of the active catalyst, which can become a serious complication during the scale-up of a cross-coupling reaction. Very often, for the in-situ generation of an active palladium catalyst, the ligand must be applied in excess, which is not optimal considering the fact that the most active phosphines and NHC ligands are normally more expensive than the palladium source. These problems were not anticipated in the beginning of the cross-coupling era but were identified and highlighted only in the last 2 decades. The solutions did not take long to emerge, and nowadays we have access to a number of structurally different pre-catalysts demonstrating exceptional activity in cross-couplings. The earliest examples of cross-coupling reactions involving organic chlorides employed bulky and electron-rich trialkylphosphine ligands, such as tritert-butylphosphine or tricyclohexylphosphine, followed by, to some extent, Buchwald's first phosphines and NHC ligands. These ligands were also the first to be incorporated into the first-generation preformed palladium catalysts. In 1995, Beller and Hermann reported the synthesis of the first preformed thermally robust palladicyl dimer catalyst based on triorthotallylphosphine and demonstrated its improved activity in coupling reactions involving chloroarene substrates. 5 years later, in 2000, Beller demonstrated the preparation and isolation of the first palladium-0 monophosphine complexes. These complexes were then tested for their performance in the Suzuki coupling of aryl chlorides. These pre-catalysts contained electron-rich, air-sensitive phosphine ligands and were more stable than the parent ligands. Notably, it was observed that the use of the well-defined preformed catalyst 4 resulted in superior results compared to the use of in-situ formed catalysts. Hermann reported the first synthesis of a preformed palladium-0 dicarbene complex 3. It was not a particularly good catalyst. Nevertheless, it formed the basis for the development of the highly active palladium Pepsi complexes. The modern preformed catalysts containing tertiary phosphine ligands can be categorized into 3 groups, depending on the nature of the generation of catalytically active monoligated palladium-0 species. The first group consists of palladium-0 catalysts with 2 bulky ligands. The monoligated palladium-0 species are generated by the dissociation of one of the bulky phosphines upon heating. Some representatives of preformed palladium-0 catalysts with 2 bulky ligands are presented here. These are coordinatively unsaturated, although they cannot adopt more bulky ligands due to steric hindrance. However, they are far more stable than corresponding free phosphines, which are normally pyrophoric. This tritert-butylphosphine palladium-0 complex is commercially available and is among the most frequently used catalysts from the list of analogous pre-catalysts. Numerous reports demonstrate the superiority of this pre-catalyst over in situ generated catalytic systems. An example supporting this was presented by Hartwig in a study on the palladium-catalyzed amination of 4-chlorotoluene. The second group of modern pre-catalysts is based on palladium-2 complexes possessing two bulky ligands. In this case, the active monoligated palladium-0 species are generated in two steps. First, dissociation of one of the bulky phosphines leads to a T-shaped palladium-2 intermediate, which is further reduced to the corresponding monoligated palladium-0 species. The sequence of these two steps can be switched. Some commercially available palladium-2 complexes possessing two bulky ligands are presented here. This group of preformed catalysts is far more stable in the presence of air compared to the previous group based on palladium-0. The bulky phosphines connected to palladium-2 can be monodentate or can be linked into a bidentate ligand, as seen in pre-catalysts 14 and 15. There are many interesting transformations enabled by these catalysts. For instance, pre-catalyst 13 can be a superior catalyst for Negishi-type couplings performed in micelles formed in water. As starting materials, researchers have used aryl bromides and alkyl halides. Organometallic reagents were formed from the reaction of alkyl halides in the metallic zinc in the micelles. The typical catalyst loading for the reaction was 2 mol%, but in some instances, it could be reduced further. The third group of pre-catalysts was developed in the group of Buchwald and is based on palladium-2 palladacicals possessing a bulky phosphine. In the presence of a base, these palladacicals undergo a reductive elimination, generating corresponding monoligated palladium-0 species and an indole derivative. They have developed several generations of pre-catalysts. The major difference between these palladacicals is that they proceed with reductive elimination at different temperatures, thus demonstrating distinct stability. While first-generation Buchwald palladacicals exhibit a wide range of reactivity in an impressive array of cross-coupling reactions, they require more forcing conditions for activation, possess a short lifetime in solution, and require a multi-step synthesis involving unstable organometallic intermediates. The second-generation palladacicals possess a more acidic aromatic amine and can be activated using a weak base at room temperature. However, larger ligands such as bretphos and tert-butyl-X-phos cannot be incorporated. The third generation of palladacicals replaces the chloride in the first and second-generation palladacicals with a less coordinating and more electron-withdrawing mesylate counteranion, allowing for the incorporation of larger ligands. Here are presented three examples: the second-generation pre-catalyst bearing Beller's phosphine and third-generation pre-catalyst with S-phos and A-phos respectively. Many more pre-catalysts are available through common chemical suppliers. Here's another good example of how advantageous pre-catalysts can be over the in-situ generated catalysts. The conversion of 4-chloroanisole in the Buchwald-Hartwig amination initiated by the catalyst generated from the mixture of palladium dibenzylidine acetone complex and X-phos was just 25%. Meanwhile, for the same reaction performed with the X-phos palladium G1 pre-catalyst, the conversion of the limiting reagent was complete. One of the most recently introduced pre-catalysts is the palladium-2 allyl complex bearing a suitable bulky ligand. These pre-catalysts were predominantly developed in the group of Colocott. These systems share some similarities with Buchwald's pre-catalysts in terms of generating catalytically active palladium-0 species. It is believed that upon heating, these systems release corresponding monoligated palladium-0 pre-catalysts through the reductive elimination of an allyl chloride or other related products. N-heterocyclic carbene ligands constitute the second major group of prominent ligands and are frequently used in the form of palladium pre-catalysts, capable of generating monoligated NHC-palladium-0 species. Palladium Pepsi complexes were introduced by the group of Oregon and are highly effective catalysts for cross-couplings involving difficult substrates. Successive generations of these versatile pre-catalysts have focused on increasing steric bulk at the ortho positions of the N-aryl group of the NHC ligand, which has been linked to improved catalyst performance. Palladium Pepsi complexes have some similarities with palladium-2 complexes possessing two bulky phosphines. In the case of palladium Pepsi complexes, the second L-type ligand is 3-chloropyridine that can dissociate easily, generating T-shaped NHC-palladium-2 species, which can be reduced to corresponding NHC-palladium-0 active pre-catalysts. Palladium-2 palladacicals possessing an NHC ligand are the second major group of pre-catalysts and were introduced by the group of Nolan. These systems have many similarities with Buchwald's pre-catalysts possessing phosphines and are commercially available. In this case, the NHC-Palladium zero active pre-catalysts are generated from reductive elimination of a carbazole derivative upon heating. Systems based on nickel are the last group of pre-formed catalysts worth mentioning, as they demonstrate very unique activities. Nickel-based complexes are normally very reactive and are more efficient than palladium systems for certain cross-coupling reactions. The enhanced activity of nickel complexes can be used to enable cross-couplings involving very unreactive substrates, such as aryl carbamates and carbonates. On the other hand, increased reactivity of nickel pre-catalysts makes them less stable, thus hampering their preparation, handling, and storage. Pre-catalysts based on nickel 2, nickel 1, and nickel 0 have all been used in successful cross-coupling reactions. Accordingly, the mechanisms of nickel-catalyzed cross-couplings can be quite different from those observed in palladium-catalyzed reactions, and among other possibilities, they can include radical intermediates. As we learned in the previous lecture, NHC ligands bind particularly well to late transition metals, which in turn leads to the formation of stable complexes. This is why most of the known stable nickel-based pre-catalysts are based on NHC ligands. Alternatively, enhanced stability can be achieved with chelating ligands. This is why the most successful phosphines used for the production of nickel pre-catalysts are bidentate phosphines. Here, in the top line, selected pre-catalysts based on nickel 2 are presented. The pre-catalysts in the middle are based on nickel 1. The catalysts on the bottom are based on nickel 0. Unfortunately, there are only a few commercially available nickel pre-catalysts. In summary, a similar relationship exists between the rapid development and innovation of cross-coupling and the evolution of mobile phone technology over the last 2 decades. One can imagine a parallel between the high-value features of state-of-the-art catalysts and the advanced features of modern mobile phones. Yet, advanced features of modern catalytic systems are not essential for less challenging cross-couplings, and less advanced but cheap catalysts still can serve a purpose. It should be noted that the holy grail in cross-coupling methodology is the development of a universal catalyst that can achieve equally high conversions, regardless of the nature of coupling partners. This still remains unachievable, despite the incremental steps taken to develop more robust and reproducible catalytic systems for specific reactions. However, by applying logic, experience, and intuition, today we are closer to predicting a few catalysts for many cross-coupling transformations. This and some other related topics will be described in the coming lectures, where the main focus will be put on the selection of appropriate catalytic systems for very unreactive substrates. Thank you for your attention. Hello everyone, and welcome back to the series of lectures on cross-couplings. So far, we have mainly focused on examining the most prominent ligands and catalysts in the field. This lecture will be devoted to describing the reactivity of the most frequently used coupling partners in cross-couplings and how the reactivity of substrates can be altered by the choice of a suitable catalytic system. Aryl halides are the most commonly used electrophilic coupling partners in cross-coupling chemistry. Numerous high-yielding methodologies exist for preparing aryl chlorides and aryl bromides, making them readily available commercial building blocks for organic synthesis. Not only are aryl chlorides and aryl bromides employed as electrophilic coupling partners, but they also serve as the most frequently utilized starting materials for the preparation of organometallics, the nucleophilic coupling partners in cross-couplings. In contrast, aryl iodides and aryl fluorides are less common and are not easily obtained from conventional reagents. For main factors control the reactivity of electrophilic coupling partners, the strength of the bond, polarity, polarizability of the carbon heteroatom bond, and steric hindrance around the bond. In highly reactive electrophilic coupling partners, the carbon heteroatom bond should not be too strong. It should be polar and polarizable, and preferably, it should not be surrounded by bulky groups. When considering these factors, we establish a general order of reactivity for aryl halides. Aryl iodides are the most reactive, followed by aryl bromides and aryl chlorides. The carbon-fluorine bond is strong and rigid, making aryl fluorides the least reactive systems for oxidative addition. Here, one can observe the periodic trends in action. Moving down the periodic table increases the polarizability of the carbon-halogen bond, rendering it more reactive for oxidative addition to the catalyst. When considering other elements, the electrophilic coupling partners are referred to as pseudohalides. Here, the group 2 elements connected to the aromatic ring are illustrated. The reactivities of these systems differ significantly from aryl halides. While carbon-oxygen and carbon-nitrogen bonds in anisols and anilines remain polar and somewhat polarizable, the carbon-carbon bond is nonpolar, and organoboron reagents are more prone to undergo transmetallation. Steric effects become crucial in this context, with the carbon heteroatom bond becoming more sterically hindered as we move left in the periodic table. Another factor significantly reducing the reactivity of anisols and anilines toward oxidative addition is the conjugation. Due to conjugation, the lone pairs of electrons at the heteroatom in anisols and anilines are shared with the aromatic system. This conjugation gives the carbon heteroatom bond a double bond character, making it more rigid, less polarizable, and stronger than single bonds. Conjugation in phenol derivatives can be minimized by substituting the oxygen with strong electron withdrawing groups. This modification can render phenol derivatives suitable electrophilic coupling partners for cross-coupling reactions. The most successful electron withdrawing groups applied to phenols are triflate, mesylate, and tosylate. Aryl triflates have proven to be excellent coupling partners in cross-couplings, exhibiting higher reactivity than aryl mesylates and tosylates, which are still useful coupling partners demonstrating comparable reactivities. Alternatively, phenols can be protected in the form of acetates, carbonates, and carbamates. However, these systems do not exhibit a notable tendency to undergo oxidative addition and require special catalysts and conditions. For aniline derivatives, conjugation can be discontinued through the preparation of ammonium salts, nitro compounds, and diazonium compounds. Diazonium compounds stand out as superior electrophilic coupling partners for cross-coupling chemistry. As you may recall, they were first applied by Meerwein, and metal-catalyzed transformations involving diazonium compounds are frequently referred to as Meerwein cross-coupling reactions. Ammonium salts are not suitable coupling partners because the introduction of the third alkyl group at nitrogen makes these systems considerably sterically hindered. Although the carbon-nitrogen bond in nitro compounds is highly polar, these systems are also not ideal coupling partners. Here, we encounter another type of conjugation where electrons are donated from the aromatic ring to the nitro group. This, in turn, imparts a partial double bond character to the carbon-nitrogen bond and increases the rigidity of the bond. Although carbon-carbon bonds are nonpolar, they can be made polar by oxidizing the methyl group. Carboxylic acids and their derivatives constitute an emerging group of coupling partners for cross-coupling chemistry. However, the mechanisms of reactions involving these substrates can differ significantly from those with aryl halides. Decarboxylations typically involve radicals and may even generate anionic intermediates similar to organometallics. Nitriles are another promising group of electrophilic coupling partners. Here, the carbon-carbon bond is polar, and the system is not particularly sterically hindered. It should be noted that research on the application of nitriles in cross-coupling reactions is still in its infancy. The sustainability and atom economy of reactions involving carbon-carbon bond activation can be questioned, as the primary goal of cross-coupling chemistry is to create carbon-carbon bonds rather than break them. Summarizing this section, it should be noted that the most reactive electrophilic coupling partners are aryl iodides and diazonium compounds. Unfortunately, they are not readily available, and additionally, diazonium compounds are explosive. The second best electrophilic coupling partners, in terms of reactivity, are aryl bromides and aryl triflates. These compounds are notably more reactive than aryl chlorides, which, in turn, are more preferable than other sulfonates. Reactions involving aryl chlorides, mesylates, and tosylates are typically facilitated by bulky and strong sigma-donor ligands. Other electrophilic coupling partners, such as acetates, nitro compounds, and derivatives of carboxylic acids, either require nickel-based catalysts or specific ligands and reaction conditions. The concluding part of this lecture will feature selected examples. Now, let's discuss organometallic coupling partners. The primary factor controlling their reactivity is the electronegativity of the metal. The less electronegative the metal, the more nucleophilic the organic subunit connected to the metal becomes. This, in turn, facilitates a more straightforward transmetallation. Another supporting factor for the transmetallation from these organometallics is that the byproduct inorganic salts, such as magnesium bromide, are not soluble in organic solvents. They usually precipitate from the reaction media, favoring the transmetallation. Organometallics based on metalloids are typically less reactive, enabling good functional group tolerance. However, these substrates often require a base for activation. It's worth noting that the base is not always necessary for organotin reagents. Now, let me describe how one can influence the activity of your coupling partners. The reactivity of an electrophilic coupling partner can be enhanced by introducing electron-withdrawing groups into the system. Conversely, the introduction of electron-donating groups effectively reduces the reactivity of the electrophilic coupling partner. Electron-withdrawing groups increase the electron deficiency of the system, subsequently enhancing the polarity of the carbon-halogen bond. Meanwhile, electron-donating groups raise the electron density in the system and increase the rigidity of the carbon-halogen bond. For example, 4-chlorobenzotrifluoride is a better coupling partner than 4-chloroanisole. Similarly, nitrophenyl triflate is more reactive in cross-couplings than aryl triflates possessing electron-donating groups. The opposite is true for organometallic coupling partners. Organometallics possessing electron-donating groups are more nucleophilic and are better substrates for transmetallation compared to those having electron-withdrawing groups. To be more specific, boronic acids equipped with methoxy groups are more reactive in Suzuki couplings than boronic acids with fluorine substituents. Organotin reagents based on electron-rich 5-membered heterocycles are better substrates in Stille coupling than organotin reagents possessing electron-withdrawing carbonyl groups. Here, it is essential to remember that the increased reactivity of organometallics based on electron-rich systems can be complicated by the instability of the systems and unwanted side reactions. In fact, some organometallics based on electron-rich 5-membered heterocycles are quite unstable. What you learned in this lecture should allow you to design your synthesis involving cross-couplings more rationally. If you are tasked to prepare this purine derivative, then you can start your retrosynthesis from the disconnection of the bond in red. For the overall efficiency of the process, you can consider the Suzuki coupling based on electron-rich trimethoxyphenyl boronic acid and electron-deficient chlorinated purine derivative depicted here. If you want to prepare the commercial drug canagliflozin, used to treat type 2 diabetes, then you can start your retrosynthesis by disconnecting the bond between thiophene and fluorobenzene. You can think about the application of the Stille coupling based on the use of electron-deficient 4-fluorobromobenzene and an electron-rich derivative of 2-tributylstanyl-thiophene. In the last section of this lecture, I want to highlight selected cross-couplings involving challenging substrates such as anisols, esters, and nitro compounds. The activation of non-traditional substrates is a hot topic in this field. In 2008, an interesting report came from the group of Chatani, describing the first Suzuki coupling using anisols instead of aryl halides. The reaction was enabled by a nickel-0 pre-catalyst combined with the bulky and strong sigma donor tricyclohexylphosphine. The reported substrate scope was quite narrow and predominantly based on polycyclic arynes possessing a methoxy group. It was suggested that oxidative addition, including fused arynes, happens more readily. Therefore, there is still room for further elaboration of this strategy. Although the reaction mechanism was not examined, it is plausible that the reaction proceeds through a typical cross-coupling mechanism initiated by the oxidative addition of the carbon-oxygen bond to the nickel-0 pre-catalyst, followed by transmetallation of the aryl group from boronic ester and reductive elimination to form the biaryl. A few years later, they could demonstrate that the limitation of predominantly using fused arynes can be overcome by the application of NHC ligands. Here, among others, you can see the comparison of the results for the reactions performed with the NHC ligand L7 with those obtained for tricyclohexylphosphine. The catalysts based on phosphine ligands were typically not active for substrates other than fused arynes. Computational studies on the mechanism of the reaction suggest that the NHC ligand makes the nickel sufficiently electron-rich, thus allowing the cleavage of the carbon-oxygen bond in simple anisols. In 2015, the group of Atami was among the first to report that esters of aryl carboxylic acids can be suitable electrophilic coupling partners for the reactions involving boronic acids. The catalytic system enabling this transformation was based on nickel acetate and a strong sigma donor but non-bulky tributylphosphine. The major drawback of the developed methodology was the need to use a very high reaction temperature. The substrate scope demonstrated in the report was also impressive, and a small portion of the products with corresponding yields is presented here. With a user-friendly and inexpensive nickel catalyst, a range of phenyl esters of aromatic, heteroaromatic, and aliphatic carboxylic acids react with boronic acids in a decarbonylative manner. They computationally examined the mechanism of the Suzuki coupling reaction. Presumably, the first step of the process is the oxidative addition of the nickel-0 pre-catalyst to the carbonyl phenoxy bond of the ester. This is noteworthy as the acyl-oxygen bond is the weakest bond in the molecule. The oxidative addition is followed by transmetallation of the aryl group from boronic acid to the nickel-2 intermediate. Surprisingly, the transmetallation is not followed by the reductive elimination of the derivative of benzophenone. Instead, the transmetallation is followed by a decarbonylation leading to intermediate F. The decarbonylation is also feasible as the insertion of arones to carbon monoxide is a reversible process. The reductive elimination predominantly happens after the decarbonylation, leading to the corresponding biaryl. The need for high temperatures in the reaction is justified by the necessity to facilitate the release of carbon monoxide from intermediate G, which possibly prevents the poisoning of the catalyst. Until 2017, nitro compounds were rare substrates for cross-coupling reactions, despite being readily available commercial substrates and common intermediates in the preparation of aryl halides by the Sandmeyer reaction. The limited use of nitro compounds in metal-catalyzed reactions is due to the nitro group acting as a mild oxidant toward low-valent transition metals, leading to nitroso compounds and other reduction products. The group of Nakao successfully overcame this limitation and achieved the coupling of nitroarenes with aryl boronic acids using a palladium Bretphos catalyst. The breakthrough was the unprecedented oxidative addition of an aryl-nitro bond toward the palladium center, embodied by the bulky Bretphos ligand. Owing to the generality of this elementary step, a wide range of nitroarenes and boronic acids could be applied for the modified Suzuki coupling. Part of the substrate scope reported in their work is presented here. They performed a set of control experiments to support the proposed mechanism of the reaction. A stoichiometric reaction of the palladium pre-catalyst and nitrobenzene in the presence of Bretphos at 60 degrees resulted in the formation of an oxidative addition product via direct cleavage of the carbon-nitro bond. The obtained palladium-2 complex reacted with an aryl boronic acid in the presence of a base at room temperature to afford the corresponding biaryl. These results support the notion that the underlying reaction mechanism includes an oxidative addition, a transmetallation, and a reductive elimination, in a manner similar to Suzuki couplings involving other electrophiles. To sum it up, in this lecture, we learned the factors controlling the reactivity of electrophilic and nucleophilic coupling partners used in cross-coupling reactions. We have estimated the reactivity of common substrates based on their stereoelectronic properties. In the end, you saw how the rational selection of the catalytic system can influence the couplings involving unreactive substrates. With the knowledge we gained here about the reactivity of coupling partners, we can move forward to discuss issues regarding the selectivity in cross-couplings. In the following lecture, you will learn about the factors controlling the regio and chemoselectivity of cross-couplings involving multifunctionalized substrates. Thank you for your attention. Hello everyone, and welcome back to the series of lectures on cross-couplings. You have been introduced to cross-coupling reactions, and in the previous lecture, we compared the reactivity of the most common coupling partners used in cross-couplings. In this lecture, I will describe the factors controlling the selectivity in transformations involving substrates with more than one reactive center. Substrates possessing multiple functional groups capable of undergoing an oxidative addition are common in complex organic synthesis. For such substrates, finding conditions for the site-selective functionalization of one position over all other positions is critical. To understand how selectivity arises in the cross-coupling of polyhalogenated arones, one must first consider the mechanism of cross-couplings. A simplistic depiction of the catalytic cycle for a transition metal-catalyzed cross-coupling reveals three key elementary steps: oxidative addition, transmetallation, and reductive elimination. Oxidative addition is the step where the electrophilic coupling partner is introduced into the catalytic cycle. For most instances, oxidative addition determines the selectivity of the process. In this step, selectivity arises due to differences in the relative electrophilicities of the carbons bound to halogen groups in the parent arene. As oxidative addition formally involves the addition of electrons to a carbon-halogen bond, the most electrophilic carbon would be expected to be the preferred site of attack. Traditionally, site-selective couplings have been achieved by employing arene electrophiles bearing multiple, non-identical halogens or pseudohalogens, such as triflates. When the selectivity is determined by the use of non-identical functional groups, it is called chemoselectivity. In this case, chemoselectivity relates to the relative bond dissociation energies of carbon heteroatom bonds, which, in turn, are associated with the polarity and polarizability of the bonds. Therefore, the site selectivity in arene electrophiles bearing multiple, non-identical leaving groups follows the general reactivity trend we learned in the previous lecture. For instance, if you try to perform a Sonogashira coupling for this multi-halogenated isothiazole with not particularly active catalysts, the reaction will first proceed at the carbon-iodine bonds. By applying higher temperatures or sterically hindered sigma donor ligands, one should be able to sequentially functionalize the carbon bearing a bromide. The site-selective functionalization becomes challenging when the parent arene bears identical halogen atoms, as there is little difference in the nature of the aryl halide bonds. The site-selective functionalization of systems possessing the same functional groups is otherwise called regioselective functionalization. In these systems, regioselective coupling at the carbon bearing one halogen atom over another depends on other factors, such as the electronic nature of the atom to which the halogen or pseudohalide is attached and the steric environment, which determines the preferred site of reactivity. Recent studies indicate that the regioselectivity of cross-couplings can also be controlled by the used ligands, solvents, and additives. All these factors, along with specific examples, will be discussed here. First, we will discuss how the electronic properties of aromatic compounds determine the regioselectivity of cross-couplings. Unless there are other factors that override electronics and perturb innate reactivity, such as strong steric influences or directing groups, electronic effects will usually guide the reaction selectivity. For six-membered aromatic systems, electronic effects from present substituents are the main factors controlling regioselectivity. To understand the electronic effects caused by electron-donating or electron-withdrawing groups, you should review your knowledge in organic chemistry of arynes. Particularly, electron-donating groups make the ortho and para positions relatively electron-rich. In such a system, if you have a halogen atom at the meta position, then the electron-donating group will drive the selectivity of cross-coupling to the meta position. For electron-withdrawing groups, the selectivity is reversed, as they make the ortho and para positions relatively more electron-deficient. As a result, electron-withdrawing groups direct oxidative addition to the ortho and para positions. In the case of aromatic heterocycles, the electronic properties of the system are controlled by the heteroatom, and as a rule, the most electron-deficient positions are alpha positions to the heteroatom. Let me show you two examples to make everything more obvious. One example of substituent effects on electronics and, by extension, guiding regioselectivity was described by Hearn and co-workers in their syntheses of unsymmetrical para-terphenyl moieties, which have been shown to possess medicinally relevant biological properties. This transformation was achieved through a sequential ligand-free Suzuki coupling of 1,4-dibromo-nitrobenzene and diverse aryl boronic acids with a palladium acetate pre-catalyst. Due to the electron-withdrawing nitro substituent, the first oxidative addition occurred preferentially at the more electrophilic carbon-bromine bond ortho to the nitro group, resulting in the ortho-substituted biaryl intermediate. Subsequently, this intermediate underwent a second coupling at the meta position upon the addition of the second structurally different aryl boronic acid to provide the desired terphenyl scaffold. Pyridines are inherently pi-deficient by virtue of the embedded electronegative nitrogen atom, which inductively withdraws electron density from positions C2 and C4. As a result, for cross-couplings of polyhalogenated pyridines, oxidative addition is also favored at the C2 and C4 positions, but this selectivity also greatly depends on specific reaction conditions, other substituents, and substitution patterns. In this example, you can see how selectivity can be achieved between the electronically similar C2 and C4 positions of 2,4-dichloropyridines by altering the substituent at the C3 position. When the substituent is equal to hydrogen, the intrinsic reactivity of this pyridine under Stille coupling conditions favors cross-coupling at the C2 position. Adding an electron-donating amino group to the C3 position also favors coupling at the C2 position, presumably due to the deactivation of the C4 position. However, adding an electron-withdrawing nitro group to C3 activates the C4 position toward oxidative addition, thus completely reversing the selectivity of the reaction. For aromatic systems containing two or more of the same type of halogen, several indicators based on experimental data have been identified to help predict the intrinsically most reactive positions for oxidative addition. For instance, analysis of the proton NMR chemical shift values of the parent non-halogenated arones can serve as a guide for predicting the site of cross-coupling reactions. The position of the most deshielded proton when substituted by a halogen will be the favored site for the first oxidative addition. Remember, the higher the chemical shift of the proton, the more electron-deficient is the carbon bound to the proton. Here are presented two examples as proof for the concept. Proton NMR of the parent non-halogenated p-chiral suggests that for this 2,3-dibromo p-chiral, the most reactive site should be position 2. This was proved to be true for the Suzuki coupling reaction presented here. For the second example, similar NMR studies proposed that position 3 should be more reactive than position 4, which was confirmed by a control Suzuki coupling. Here, more examples are presented for the use of NMR prediction of the regioselectivities for 5-membered, 6-membered, infused heterocycles. The numbers show the proton NMR chemical shift values of the parent non-halogenated arones. Based on these numbers, the positions indicated in blue should be the sites for the first oxidative addition. The positions indicated in red are the second favored positions for corresponding couplings. The positions in green are the most electron-rich positions and are the least favored sites for oxidative addition. Whereas the relative carbon electrophilicities in an aromatic ring play a prominent role in oxidative addition selectivity, one must also consider the steric environment and its effect on regioselectivity. In cross-coupling, selectivity is often governed by the interplay between electronics and sterics, with the most electrophilic and most sterically accessible position being primed for oxidative addition. Among others, sterics can differentiate between two electronically similar positions, and steric effects can reinforce the selectivity dictated by innate electronics. One example of steric effects overriding electronic effects is underlined in red, where coupling takes place at the more sterically accessible C5 position of 2,5-dibromofurane. Despite the C2 position being electronically favored by the virtue of being adjacent to both an oxygen atom and an electron-withdrawing ester moiety. In the case of 2,5-dibromothiophenone underlined in blue, there are no pronounced electronic effects from the pendant tetrahydroisoquinoline derivative. Therefore, the C2 and C5 positions are electronically similar, and in this case, the difference in the steric environments between these two positions facilitates reactivity at the more sterically accessible C5 position. The C2 positions of thiols underlined in green are both electronically preferred over the C5 and C3 positions and are more sterically accessible. Therefore, sterics reinforce the innate electronics of these systems, and coupling occurs at the C2 position in both cases. The extra functional groups present in polyhalogenated substrates, among others, can have coordinating ability to the catalyst and can act like a directing group, guiding the catalyst to a proximal carbon heteroatom bond, thus enabling regioselective oxidative addition and subsequent functionalization. The functional groups on the polyhalogenated substrate can also coordinate to the ligand of the catalyst and guide the catalyst to the position for oxidative addition through the ligand of the catalyst. The transition metal binding directing groups are optimal for proximal carbon heteroatom bond cleavage, whereas ligand binding directing groups can be applicable for remote carbon heteroatom bond cleavage. Let me show you a few examples for clarity. Basic nitrogen-containing heterocycles are a common class of transition metal binding directing groups for the selective functionalization of polyhaloarenes. For instance, nickel-catalyzed Negishi coupling, including perfluorinated arones, can be made regioselective by the application of directing groups based on pyridine, quinoxalin, and oxazolene. The ligand-binding directing group strategy is particularly useful for substrates possessing functional groups that cannot act as transition metal binding directing groups. For instance, phenols are not particularly good ligands for late transition metals. However, they are capable of forming heteroaggregates with specialized phosphine ligands possessing a hydroxyl group, as presented here. These non-covalent interactions can place the palladium catalyst in close proximity to the carbon-halogen bond in the ortho position of phenol, thus enabling regioselective Sonogashira coupling followed by cyclization. Certain ligands that have adequate length and can bind to a functional group present in the substrate serve as a linker between the substrate and the transition metal complex, enabling the catalyst to come in reasonable proximity to the remote carbon-halogen bond for activation. Non-covalent interactions involving sulfonylated phosphines in the amino group of polychlorinated systems, as presented here, can be applied for the regioselective Suzuki coupling at remote positions. The regioselectivity of the reaction can be controlled by the position of the sulfonyl group. The best selectivity for the meta-arylation product was obtained when using the sulfonylated derivative of S-phos combined with palladium acetate. Another factor affecting selectivity was the substituent at the amino group. More polar substituents like triflate enhance the electrostatic interactions between the ligand and the amino group, improving the meta-selectivity of the reaction. Reactions performed with non-sulfonylated ligands resulted in a statistical mixture of regioisomers, supporting the proposed hypothesis on the control of regioselectivity by non-covalent interactions. The majority of examples for the site-selective cross-coupling of polyhalogenated arones discussed so far have leveraged key differences in reactivity between various carbon heteroatom bonds and the directing abilities of functional groups present on the substrate. Alternatively, ligands that bind exclusively to the transition metal can be used to tune the electronic and steric properties of the catalyst, thus controlling the regioselectivity of a given cross-coupling involving polyhalogenated substrates. In other words, the right ligand-transition metal combination can define the regioselectivity of cross-couplings regardless of the steric and electronic nature of the used starting materials. The reasons controlling the regioselectivity enabled by a certain ligand are not always clear. Here is a good example describing a ligand-controlled site-selective Suzuki coupling of 3,5-dichloropyridazine. The reaction can produce a mixture of three products, including the biaryl formed by the arylation at position C3, the product from arylation at position C5, and diaryl pyridazine produced by double arylation. Based on the electronic properties of the system, 3,5-dichloropyridazine is expected to react more readily at position C3, as the bond dissociation energy of the carbon-chlorine bond alpha to the nitrogen atom is lower. Screening a wide range of ligands indicated that electron-deficient bidentate ligands and triphenylphosphine favor the formation of the C3 coupled product. The best yield and selectivity were achieved using the DPPF ligand. Notably, an electron-rich analog of DPPF gave the opposite selectivity, albeit in a moderate ratio between mono and bis-coupled products. This prompted the authors to screen more electron-rich monodentate phosphines. As a result, it was found that Buchwald's biaryl monophosphine ligands predominantly favor the formation of the bis-coupled product, while Q-phos gave the best selectivity for the C5 coupled product. It was hypothesized that electron-deficient ligands favor slower oxidative addition. Therefore, the insertion of the metal occurs at the more reactive C3 position, as predicted by the electronic properties of pyridazine. On the contrary, bulky electron-rich ligands direct the metal center to insert into the more accessible C5 position, as the lone pairs at nitrogens form a nucleophilic pool shielding the position C3 for the electron-rich catalytic system. Altering the used ligand is not the only factor that can potentially control the regioselectivity of cross-couplings. The first example of shifting the regioselectivity by modifying only the reaction solvent was disclosed in 2008. In a Suzuki coupling between dibromopyrrole and 4-methoxyphenylboronic acid, in a 3-to-1 mixture of toluene and ethanol, a mixture of isomer arylation products was obtained in a ratio of 22-to-1, with the C5 coupled product isolated in 70% yield. Alternatively, when the reaction solvent was changed to DMF, the C3 coupled product was obtained in 53% yield. In general, it was found that under otherwise identical conditions, more polar solvents such as DMF and DMSO favor C3 coupling, whereas relatively less polar solvents favor C5 coupling. NMR studies indicated that the electronics of C3 and C5 positions changed depending on the differential solvation. In nonpolar solvents, the difference in proton NMR chemical shifts between the C3 and C5 protons was barely detectable, while in DMSO, the difference between the C3 and C5 protons was more pronounced, with the C3 proton remaining more deshielded. Given that oxidative addition is generally favored at the more electron-deficient positions, these NMR studies were in good agreement with the experimentally observed selectivity trends. In a related study on the Suzuki coupling involving 3,5-dibromopyrrone, it was found that in nonpolar solvents, the reaction delivers the C3 coupled product. On the contrary, in more polar solvents, such as DMSO and DMF, and in the presence of copper iodide, the C5 coupled product was generally formed as the major product. Notably, the C5 coupled product was observed only in the presence of copper iodide, and conducting the reaction in the absence of copper iodide exclusively generated the C3 coupled product. Control experiments on the oxidative addition of palladium to 3,5-dibromopyrrone were consistent with the Suzuki coupling results. The C3 palladium complex was formed in nonpolar solvents like toluene, irrespective of whether copper iodide was added. In polar solvents like DMF, the C5 palladium complex was formed only in the presence of copper iodide. Computational studies indicate that copper iodide assists in the dissociation of phosphine ligands from palladium, leading to monoligated palladium species, which are more reactive and can initiate, among other things, oxidative addition at the less reactive C5 position. Chemoselective reactions, which discriminate between electrophiles such as organohalides, are well established. In contrast, the development of nucleophile selective reactions has seen limited success. Nevertheless, modern discoveries in the field of organoboron chemistry provide us with effective tools that can enable site-selective coupling in systems possessing multiple carbon-boron bonds. As you may remember, for transmetallation involving organoboron reagents, one needs to use a base to activate the boron. Boronic acids and their esters have an empty p orbital at the boron and behave like Lewis acids. The applied base coordinates to the empty p orbital of boron, increasing the nucleophilicity of the system and facilitating transmetallation. The key for a successful boron-selective reaction is to discriminate between the boronyl groups that are exposed to the same reaction conditions. Appropriate use of masking groups on the boron atoms can play a critical role in controlling their reactivity. So far, 2 efficient masking groups were introduced for boronic acids. One is based on 1,8-diaminonaphthalene and is abbreviated like DAN. The other is based on N-methylamino-diacetic acid and is abbreviated like MEDA. These masking groups reduce the Lewis acidity of boron by delocalization of electrons from lone pairs of nitrogens to the empty p orbital of the boron. This, in turn, protects the boron from reactions involving bases and prevents transmetallation. DAN and MEDA masking groups are stable under basic conditions, which are typical for most of the cross-couplings. On top of that, these masking groups can be removed at any point by acidic hydrolysis, generating free boronic acids that can be applied for later functionalization. Here is an example of chemoselective Suzuki couplings involving multiple organoboron reagents. Treatment of an aryl boronic acid with an aryl bromide possessing boron masked with a diaminonaphthalene group will lead to a single product where the boron masked with diaminonaphthalene will stay intact. Later, the diaminonaphthalene protecting group can be removed by acidic hydrolysis, and the formed boronic acid can undergo another Suzuki coupling to deliver this terphenylene derivative. This approach has some similarities to peptide synthesis and is ideally suited for manual or automated generation of diverse polyurenes. Here is an example covering the N-methylamino-diacetic acid masking group. N-methylamino-diacetic acid-protected aryl boronic acid can undergo a selective CH borylation catalyzed by iridium. The newly introduced pinacol ester of boronic acid can be consumed in a consecutive Suzuki coupling without affecting the masked boron. In summary, while the chemoselective functionalization of a carbon-halogen bond in a molecule bearing multiple distinct halogens can be quite straightforward, predicting and rationalizing the selectivity outcome in an arene bearing multiple, but identical halogen atoms has remained challenging. Therefore, several factors have been identified to enable differentiation between carbon positions bearing identical halogen atoms. Initially, this distinction was achieved purely by leveraging the inherent electronics of the system, where the most electrophilic carbon-halogen bond would undergo faster oxidative addition. In addition to electronically driven regioselective cross-coupling processes, steric effects were also identified to guide oxidative addition to the least sterically encumbered carbon position. Following these advances, the coordinating ability of functional groups present in the substrate was leveraged to direct oxidative addition to a particular position. Subsequently, methods were developed to achieve regioselectivity by tuning the electronic and steric influences of an external ligand. More recently, selectivity has been achieved by altering the choice of reaction solvents and additives. The following lecture will demonstrate how the knowledge you have gained up to this point can be applied in the production of value-added products. Thank you for your attention. Greetings to all, and welcome back to the last part of a series of lectures on cross-couplings. By now, you must be well aware of the main principles covering cross-coupling reactions. In this section, I will demonstrate selected applications of cross-couplings, including selective multifunctionalization as well as the synthesis of natural products, agrochemicals, pharmaceuticals, and materials. I want to start with a remarkable transformation developed in the group of Catalani. They have found that when a cross-coupling reaction involving aryl halides is conducted in the presence of bicyclic olefins like norbornene, the reaction ends up with the formation of a polyfunctionalized product. Starting from a monofunctionalized aryl halide, it is possible to obtain a 1, 2, 3 tri-substituted arene in good yields and selectivity. To understand what is going on here, one should briefly go through the mechanism of the reaction. The Catalani reaction begins with the oxidative addition of a palladium-0 pre-catalyst to the aryl halide. The generated palladium-2 species undergo an insertion, including norbornene. In the insertion product, β-hydride elimination is not possible, as one of the beta protons is unable to adopt a syn conformation with palladium, while the other is at the bridgehead of a bridged ring and cannot eliminate, as that would create an sp2 hybridized carbon at the bridgehead, significantly increasing the strain in norbornene. Instead, the inserted norbornene directs palladium to the ortho-CH bond and initiates a regioselective CH activation, which will be discussed in detail in the next module. The formed palladicycle can then undergo another oxidative addition with an electrophilic coupling partner present in the reaction media, forming a palladium-4 intermediate presented here. Palladium-4 species are normally unstable and revert to the palladium-2 insertion products to norbornene by a reductive elimination. The reductive elimination forms the first carbon-carbon bond, and if the R group ortho to the insertion site is a proton, then the CH activation sequence can start again and can lead to the second carbon-carbon bond-forming event. After the functionalization of ortho positions, the main stabilization pathway for the palladium-2 species shown here is the reverse process to norbornene insertion, which can also be called a beta-carboanion elimination. Norbornene insertion is a reversible process, which means that it can be used in catalytic quantities. After the elimination of norbornene, the generated palladium-2 species can proceed to a transmetallation event if there is an organometallic reagent present or another insertion if there are other olefins available. The transmetallation can end with the reductive elimination generating the tri-substituted product and the active pre-catalyst, while olefin insertion can lead to the het coupling product and the active pre-catalyst. The Catalani reaction has found many implications in organic synthesis. For instance, linoxepin is a polysubstituted aromatic natural product from the lignan family and has long been used for the treatment of pain, rheumatoid arthritis, and warts. The Catalani reaction has proven to be an effective method for the selective polyfunctionalization of arenes used in the synthesis of linoxepin and its analogs. The key step in the total synthesis of linoxepin is presented here. It is based on the use of the Catalani reaction for the regioselective double functionalization of intermediate 5 with an alkyl iodide and an acrylate. In the following step, the introduced olefin was oxidatively cleaved to an aldehyde, which was followed by an aldol cyclization with gamma-butyrolactone. The last step of the synthesis was the intramolecular het coupling, leading to linoxepin. Other cross-couplings are also extensively used in the synthesis of natural products. Here, the structure of vancomycin, a natural antibacterial cyclic peptide, is presented. One of the key steps in the total synthesis of vancomycin was the construction of the underlying biaryl moiety. The group led by Niccolò was the first to report the full total synthesis of vancomycin. In their approach, the biaryl moiety was constructed through the palladium-catalyzed Suzuki coupling shown here. The rotation around the newly formed carbon-carbon bond is constrained due to steric hindrance, leading to the formation of 2 diastereomers in a 2-to-1 ratio. The diastereomers were separated before proceeding to the next steps of the synthesis. In another report, following shortly after the work from the group of Niccolò, Boger and his colleagues applied a similar strategy to forge the crucial biaryl linkage. However, in this case, they obtained an almost 1-to-1 ratio for the diastereomeric biaryls. Another report from the group of Niccolò demonstrated the total synthesis of sangliferin A based on multiple cross-couplings. The cornerstone of the devised synthetic strategy was the proposed late-stage regioselective Stille macrocyclization of bisphenol iodide precursor to generate the 22-membered ring intermediate, to which the complex spirolactam side chain would be appended through a second Stille coupling process. The first Stille coupling was an intramolecular process and led to the formation of the 22-membered ring in 62% yield and complete stereoselectivity. The regioselectivity of the macrocyclization was controlled by sterics, with only the least sterically hindered vinyl iodide participating in the coupling. The second Stille coupling was based on the use of the newly formed macrocycle possessing the second vinyl iodide moiety in the previously prepared spirolactam side chain equipped with an alkenyl stannane subunit. Both couplings were enabled by a palladium catalyst combined with triphenylarsine used as a ligand. The dimeric alkaloid psychotetramine can be synthesized by an impressive example of a palladium-catalyzed carbon-nitrogen coupling reaction. The formation of this bond represents a very challenging interrelation as it involves two highly hindered fragments, an ortho-substituted aryl bromide and an alpha-substituted indole. Moreover, the reaction is highly regioselective, leaving two additional NH groups unprotected. After thorough optimization of the reaction conditions, a rufose-based catalyst provided the best yield for the interrelated product. Attempts to improve the result by employing an excess of the nucleophile or slow addition of the catalyst were unsuccessful. Only the use of an excess of aryl bromide was beneficial to the yield, which, however, was not cost-effective. The synthesis of a wide range of agrochemicals includes at least one step based on cross-couplings. For instance, bixafen is a fungicide developed by Bayer and is used for the treatment and prevention of various leaf diseases. It is produced by a sequence of transformations starting with the palladium-catalyzed Sonogashira coupling presented here. The alkylation is followed by a Diels-Alder reaction to construct the second phenyl ring of the key intermediate in the synthesis. Another elegant route is based on the Suzuki coupling between dichlorophenyl boronic acid and the derivative of 2-bromoacetanilide. The Suzuki coupling is enabled by the tritert-butylphosphine ligand. Bifenazate is an insecticide used for mite control. The synthesis of bifenazate is based on the Buchwald-Hartwig amination, including the derivatives of biaryl bromide and hydrazine. The carbon-nitrogen bond formation is enabled by BiNAP combined with palladium acetate. Over the last 3 decades, cross-couplings have become a reliable and indispensable tool for the synthesis of pharmaceuticals. This development was predominantly influenced by the advancement of modern phosphines, NHC ligands, and preformed catalysts. I want to start with an example of how cross-couplings contribute to the discovery of new antibiotics. For instance, antibiotics based on 4-quinolone as a key structural motif contain a piperazine core. Various modifications to the piperazine core can introduce new chemical, structural, and biological properties into the drug backbone. With this in mind, Beatty and colleagues prepared a number of ciprofloxacin analogs by incorporating derivatives of piperazine into the 4-quinolone backbone. For this purpose, they applied a chemoselective Buchwald-Hartwig amination built on chlorinated 4-quinolones. The cross-coupling reactions occurred most efficiently with BiNAP as a supporting ligand. Here is another example reported by Amgen on the multi-kilogram preparation of thalazine, which is used for the treatment of inflammatory conditions such as rheumatoid arthritis and psoriasis. The key step in the synthesis was based on the Suzuki coupling involving thalazine chloride and this boronic acid. They managed to obtain the product of the coupling on a 5-kilogram scale with a 90% yield. The main side reaction of the process was the proto-deboronation of the boronic acid, as the reaction was performed in protic solvents. However, this side process could be minimized by the application of S-phos as a ligand. The key intermediate of the synthesis was purified by recrystallization and transformed into the final product through amidation. S-phos is one of the prominent ligands in the field, and the high activity of the catalytic system based on S-phos enabled a very low catalyst loading for this multi-kilogram scale process. Scientists from Pfizer reported the kilogram scale synthesis of the highlighted multifunctionalized arene using multiple Heck couplings. This new drug candidate can be used for the treatment of asthma, unstable angina, deep vein thrombosis, and coronary atherosclerosis. Taking advantage of the difference in reactivity between aryl iodides and aryl bromides under Heck reaction conditions, the researchers from Pfizer chemoselectively coupled this polyhalogenated substrate and ethyl acrylate at the iodide. The product of the first Heck coupling was formed in a 79% yield after crystallization from methanol. GCMS analysis of the crude mixture showed that the yield of the bisacrylation byproduct, formed from the olefination at bromide, was only 0.4%. Subsequently, the product of the first olefination was coupled at the bromide with N-vinyl phthalimide in a second Heck reaction performed at an elevated temperature in xylene used as a solvent. Remarkably, the yields of both Heck couplings were reproducible in the absence of phosphine ligands. Cross-couplings are frequently used in the preparation of monomers for the production of value-added polymers. For instance, the highlighted functionalized acrylate can be used to produce self-healing polymers with sensing attributes. The functionalized acrylate was prepared by applying the Buchwald-Hartwig amination between this spirocyclic chlorinated arene and an acrylate possessing an amino group. The reaction was enabled by a palladium catalyst based on Beller's diatomantyl embutylphosphine. Azaicines highlighted here are commonly employed as structural core units in numerous organic transistors and organic light-emitting diode materials. Following an approach based on the Buchwald-Hartwig amination involving bisaryl halides and bisanilines, Bunz and colleagues prepared the first stable diazaheptacines. For this purpose, they applied a highly active preformed palladium catalyst based on Rufos in the first-generation palladicycle introduced by the group of Buchwald. In another study reported by the group of Kido, the Buchwald-Hartwig amination was used to introduce a series of fluorescent dyes into organic light-emitting diodes. The fluorescent dyes were synthesized through palladium-catalyzed double carbon-nitrogen bond-forming reactions between derivatives of bromofluorine and aminopyrroline. For this reaction, they applied the original conditions based on the use of the DPPF ligand developed by Hartwig. Many related studies on the use of cross-couplings for the invention of materials can be found in thematic journals on materials sciences. To sum it up, in this module, you have learned about the most important cross-coupling reactions. We systematically examined the most successful phosphine and NHC ligands, as well as preformed catalysts used in cross-couplings. We explored the activity pattern and common substrates applied in couplings and the factors determining selectivity in cross-couplings. Finally, we briefly covered several specific applications of cross-coupling technologies. All the best with your midterm evaluations and see you in the next module.